Hi guys, welcome to this video. So in this video, I'm going to explain you the system design topics which are commonly asked in system design interviews, and also it will be useful for designing software systems efficiently. So I've just taken these topics from several sources and also from system design primer, and I have asked ChatGPT to give me the description of these topics in 250 words or less. So I'm just taken this information and created a video. Yeah, so as you can see, I have just created, just taken that information and I have just read out all this information which ChatGPT has given to me. So I have put the static images and I have explained the topics. So there, you might see some redundant information in these topics. Like, there are several sentences which ChatGPT has given which are redundant. So please ignore that, guys. So please go through this video. You can see that there are around 23 to 24 topics, and this covers a lot, and I will try to. So yeah, in upcoming videos I'll try to explain this in detail. So as of now, I just taken that information from ChatGPT and created this video. So please ignore the mistakes, guys. Yeah, thank you. Scalability is an essential concept in software engineering that refers to a system's ability to handle increased workloads or traffic without compromising performance. In other words, a scalable system can handle a growing number of users or data without slowing down or crashing. There are two primary techniques for achieving scalability: horizontal and vertical scaling. Horizontal scaling involves adding more servers or nodes to a system, while vertical scaling involves increasing the resources of individual servers. Horizontal scaling is commonly used in web applications where traffic can fluctuate significantly, and the ability to scale up or down quickly is essential. Vertical scaling is typically used in database servers where improving individual server resources can provide better performance and scalability. Both horizontal and vertical scaling have their advantages and disadvantages. Horizontal scaling can provide better fault tolerance and availability by distributing the workload across multiple servers, but it can also increase complexity and require more management overhead. Vertical scaling can provide better performance and scalability by improving the resources of individual servers, but it can also be expensive and have limits on how much a single server can be scaled. Scalability is crucial for systems that are expected to handle large amounts of data or traffic, such as social media platforms, e-commerce websites, and financial systems. Failure to design a scalable system can result in slow performance, downtime, and ultimately loss of customers or revenue. Therefore, it is essential to consider scalability from the outset of a project and design a system that can handle increased loads or as the business grows. Latency is the amount of time it takes for a system to respond to a user's request. In software engineering systems design, latency is an important concept as it directly impacts the user experience. The lower the latency, the better the user experience. Latency can be affected by various factors such as network speed, server processing time, and bandwidth. In order to minimize latency, software engineers must consider the system design from the outset of the project. One way to minimize latency is to use a content delivery network, which can store copies of frequently accessed data in different locations around the world. When a user requests data, the CDN can serve the data from the nearest location, reducing the time it takes to deliver the data to the user. Another way to minimize latency is to optimize the system's code and database queries. This can be achieved by reducing the number of requests to the server, minimizing the size of the data being sent, and optimizing the database queries. Latency can also be reduced by implementing caching mechanisms that store frequently accessed data in memory, allowing the system to respond quickly to subsequent requests. In summary, latency is a critical concept in software engineering systems design as it impacts the user experience. Minimizing latency requires considering the systems design from the outset of a project, optimizing systems code and database queries, and implementing caching mechanisms and CDN to serve data from the nearest location. By minimizing latency, software engineers can improve the user experience and ensure the system is performant, efficient, and reliable. Throughput and bandwidth are the two important concepts in software engineering systems design that relate to a system's ability to handle data traffic. Throughput refers to the amount of data that a system can handle in a given time period. It is typically measured in bits per second or bytes per second. In order to achieve high throughput, software engineers must design a system that can effectively handle large amounts of data traffic, which can be achieved through techniques such as load balancing, content delivery networks, and caching. Bandwidth, on the other hand, refers to the maximum amount of data that can be transferred over the network connections in a given time period. It is typically measured in bits per second or bytes per second. Bandwidth can be a limiting factor in achieving high throughput, as the system can only handle as much data traffic as the available bandwidth allows. Software engineers must consider both throughput and bandwidth when designing a system. To achieve high throughput, they must design a system that can efficiently handle large amounts of data traffic and optimize the system's code and database queries. To maximize bandwidth, they must ensure that the system is using the most efficient network protocols and that the network infrastructure can support the system's data traffic. In summary, throughput and bandwidth are two important concepts in software engineering systems design that relate to a system's ability to handle data traffic. To achieve high throughput, to handle data traffic, and next, in order to achieve high throughput, software engineers must design a system that can efficiently handle large amounts of data traffic. While to maximize bandwidth, they must ensure that the system is using the most efficient network protocols and that the network infrastructure can support the system's data traffic. In software engineering systems design, availability and consistency are two important concepts that are often in tension with each other. The CAP theorem, named after these concepts, is a fundamental principle in distributed computing that states that a distributed system can only provide two of the following three guarantees: consistency, availability, and partition tolerance. So, availability refers to a system's ability to respond to user requests and remain operational, even in the face of failures or high traffic volumes. In other words, an available system is one that is always up and running and can continue to operate even if some of its components fail. To achieve high availability, software engineers must design a system that is resilient, fault tolerant, and able to handle unexpected failures. Consistency, on the other hand, refers to a system's ability to provide the same data to all the users at the same time, regardless of where they are accessing the system from. In other words, a consistent system is one where all the users see the same data at the same time. Achieving consistency can be challenging in a distributed system, as data must be replicated across multiple nodes and kept in sync. The CAP theorem states that in a distributed system, it is impossible to provide all three guarantees of consistency, availability, and partition tolerance at the same time. Instead, software engineers must choose which two guarantees are most important for the system and optimize the system design accordingly. In summary, availability and consistency are two important concepts in software engineering system design that are often in tension with each other. The CAP theorem states that in a distributed system, it is impossible to provide all the three guarantees of consistency, availability, and partition tolerance at the same time. Software engineers must choose which two guarantees are most important for the system and optimize the system design accordingly to achieve the desired level of availability, consistency, and partition tolerance. The domain name system, DNS, is a critical component of the internet that translates names into IP addresses. In software engineering systems design, DNS plays an important role in ensuring that users can access websites and other online services. When a user types a domain name into their web browser, the browser sends a request to a DNS server to resolve the domain name into an IP address. The DNS server then returns the IP address to the browser, which uses it to connect to the appropriate web server and retrieve the requested content. The DNS system is hierarchical, with multiple levels of domain names, including the top level domains TLDs, second level domains, and subdomains. Each domain name is registered with a domain name registrar and can be managed by its owner. In terms of software engineering systems design, DNS is important because it can affect the performance, reliability, and security of a system. For example, a poorly configured DNS server can result in slow page load times or even downtime, which can impact the user experience and business revenue. To ensure that the DNS system is performant and reliable, the software engineers must design a system that is scalable, fault tolerant, and secure. This can be achieved by implementing multiple DNS servers, using load balancing to distribute traffic across them, and configuring the DNS servers to cache frequently accessed data. Security is also a critical consideration in DNS design, as DNS can be vulnerable to various types of attacks such as DNS spoofing and DNS amplification attacks. Software engineers must ensure that the DNS system is protected against these types of attacks by implementing security measures such as DNS SAC and DDoS mitigation techniques. In summary, the domain name system DNS is a critical component of internet that translates domain names into IP addresses. In software engineering systems design, DNS plays an important role in ensuring that the users can access websites and other online services. To ensure that the DNS system is performant, reliable, and secure, software engineers must design a system that is scalable, fault tolerant, and secure, and implement security measures such as DNS SAC and DDoS mitigation techniques. Content delivery network. CDN is a system of servers that are distributed across the world and work together to deliver content to users quickly and efficiently. In software engineering system design, CDNs play an important role in improving the performance and reliability of the web applications and other online services. When a user requests content from a web application or other online service, the request is routed to nearest CDN server, which delivers the content to the user. This reduces the distance from the content This reduces the distance from the content must travel and can result in faster page load times and improved user experience. CDNs can also provide other benefits such as improved reliability and availability. By distributing content across multiple servers, CDNs can ensure that the content remains available even if some server fail or become overloaded with traffic. In terms of software engineering systems design, CDNs must be designed to be scalable, fault tolerant, and secure. This can be achieved by implementing multiple CDN servers, using load balancing to distribute traffic across them, and configuring the CDN servers to cache frequently accessed data. Security is also a critical consideration in CDN design, as CDNs can be vulnerable to various types of attacks such as DDoS attacks and data breaches. Software engineers must ensure that the CDN system is protected against these types of attacks by implementing security measures such as SSL or TLS encryption, access control, and intrusion detection. In summary, a content delivery network CDN is a system of servers that work together to deliver content quickly and efficiently to users. In software engineering systems design, CDNs play an important role in improving the performance and reliability of web applications and other online services. To ensure that the CDN system is scalable, fault tolerant, and secure, software engineers must design a system that uses multiple servers, load balancing, and security measures such as SSL, TLS, encryption, and access control. A load balancer is a device or software that distributes network traffic across multiple servers to ensure that no single server is overwhelmed with requests. In software engineering systems design, load balancers play an important role in improving the performance, availability, and reliability of web applications and other online services. When a user requests content from a web application or other online service, the request is routed to a load balancer, which distributes the request across multiple servers. This ensures that each server handles an equal share of the workload and can prevent any one server from becoming overloaded or failing. Load balancers can also provide other benefits, such as improved scalability and flexibility. By distributing traffic across multiple servers, load balancers can handle large amounts of traffic and can be easily scaled up or down as needed. In terms of software engineering systems design, load balancers must be designed to be scalable, fault tolerant, and secure. This can be achieved by implementing multiple load balancers, using health checks to ensure that the servers are available and responsive, and configuring the load balancer to distribute traffic based on various factors such as server capacity and geographic location. Security is also a critical consideration in load balancer design, as load balancers can be vulnerable to various types of attacks such as DDoS attacks and data breaches. Software engineers must ensure that the load balancer system is protected against these types of attacks by implementing security measures such as SSL, TLS, encryption, access control, and intrusion detection. In summary, a load balancer is a device or software that distributes network traffic across multiple servers to ensure that no single server is overwhelmed with requests. In software engineering systems design, load balancers play an important role in improving the performance, availability, and reliability of web applications and other online services. To ensure that the load balancer system is scalable, fault tolerant, and secure, software engineers must design a system that uses multiple load balancers, implements health checks, and uses security measures such as SSL slash TLS encryption and access control. A proxy server is a device or software that acts as an intermediary between clients and servers. In software engineering systems design, there are two types of proxy servers: forward proxies and reverse proxies. A forward proxy server is a server that clients use to access other servers on the internet. When a client makes a request to a forward proxy server, the proxy server forwards the request to the destination server on behalf of the client. This can be useful for clients who are behind a firewall or who want to access servers that are restricted by network policies. A reverse proxy server, on the other hand, is a server that sits between clients and servers and receives incoming requests from the clients on behalf of the servers. When a client makes a request to a reverse proxy server, the proxy server forwards the request to the appropriate server based on the various criteria such as load balancing or geographic location. This can be useful for servers that are overloaded with requests or for servers that need to be hidden from clients for security reasons. In terms of software engineering systems design, reverse and forward proxies must be designed to be scalable, fault tolerant, and secure. This can be achieved by implementing multiple proxy servers, using load balancing to distribute traffic across them, and configuring the proxy servers to cache frequently accessed data. Security is also a critical consideration in proxy server design, as proxy servers can be vulnerable to various types of attacks such as DDoS attacks and data breaches. Software engineers must ensure that the proxy server system is protected against these types of attacks by implementing security measures such as SSL, TLS encryption, access control, and intrusion detection. In summary, reverse and forward proxy servers are intermediary servers that can improve the performance, availability, and security of software engineering system design to ensure that the proxy server system is scalable, fault tolerant, and secure. And software engineers must design a system that uses multiple proxy servers, implements load balancing, and uses security measures such as SSL, TLS, encryption, and access control. Databases are a critical component of software engineering systems design, providing a structured way to store and retrieve data. There are two main types of databases: SQL, structured query language databases, and NoSQL databases. SQL databases are based on a relational model where data is organized into tables with a defined schema. SQL is a standardized language that is used to interact with these databases, allowing users to create, update, and query data. SQL databases are often used for applications that require complex data structures or require data to be consistent across the different tables. NoSQL databases, on the other hand, are designed to handle large volumes of unstructured or semi-structured data. Unlike SQL databases, NoSQL databases do not use a fixed schema and instead allow for more flexible data models. NoSQL databases are often used for applications that require high performance, scalability, and availability, such as social media platforms or e-commerce websites. In terms of software engineering systems design, the choice is between SQL and NoSQL databases, depending on the specific requirements of the application. SQL databases are well suited for applications that require complex data structures and require data to be consistent across different tables. NoSQL databases are better suited for applications that require high performance and scalability and can handle large volumes of unstructured or semi-structured data. Regardless of type of database, software engineers must design the database schema and optimize database queries to ensure that the database is performant and efficient. This can be achieved by using indexing, partitioning, and other techniques to reduce the amount of data that needs to be searched. Security is also a critical consideration in database design, as databases can be vulnerable to various types of attacks such as SQL injection and data breaches. Software engineers must ensure that the database system is protected against these types of attacks by implementing security measures such as access control, encryption, and intrusion detection. In summary, databases are a critical component of software engineering systems design, providing a structured way to store and retrieve data. SQL databases are based on a relational model and are well suited for applications that require complex data sets, while NoSQL databases are designed to handle large volumes of unstructured or semi-structured data. To ensure that the database system is performant, efficient, and secure, software engineers must design the database schema, optimize database queries, and implement security measures such as access control and encryption. Database sharding is a technique used in software engineering systems design to partition large databases into smaller, more manageable pieces. In a sharded database system, each shard is stored on a separate server or set of servers, allowing for improved scalability and performance. When a database becomes too large to be efficiently managed by a single server, software engineers can use database sharding to divide the database into smaller pieces, with each shard containing a subset of data. The sharding process typically involves choosing a shard key which determines how data is distributed among the different shards. Sharding can provide several benefits for software engineering systems design, including improved scalability, performance, and fault tolerance. By dividing a large database into smaller pieces, sharding can improve query performance by reducing the amount of data that needs to be searched. Sharding can also improve fault tolerance as a failure in one shard does not affect the other shards. However, sharding can also introduce some challenges in software engineering systems design. For example, sharding can complicate database schema design and can require complex query routing and load balancing logic. Additionally, sharding can make it more difficult to maintain consistency across database as data may need to be replicated across multiple shards. To implement database sharding in software engineering systems design, software engineers must carefully design the shard key and the database schema and implement query routing and load balancing logic to ensure that data is distributed evenly across different shards. They must also implement the replication and consistency mechanisms to ensure that the data is consistent across different shards. In summary, database sharding is a technique used in software engineering systems designed to partition large databases into smaller, more manageable pieces. It can improve scalability, performance, and fault tolerance, but can also introduce challenges such as complex schema design and query routing. To implement database sharding, software engineers must carefully design the shard key and the database schema and implement replication and consistency mechanisms to ensure that the data is consistent across different shards. In software engineering systems design, cache is a mechanism used to improve the performance of applications by storing frequently accessed data in a fast, temporary storage area. The cache can be implemented at different levels of a system, such as in memory, on disk, or in a distributed network. When an application needs to access data, it first checks the cache to see if the data is already stored there. If the data is found in the cache, it can be quickly retrieved without needing to access the original data source. This can significantly improve the performance of applications by reducing the amount of time spent accessing and retrieving data. Cache can be implemented in different ways, such as with a key value store or with an object cache. Key value stores allow data to be accessed using a unique key, while object cache stores entire objects in a memory for faster access. In distributed systems, cache can be implemented using a distributed cache, where cache data is stored across multiple nodes in a network for improved performance and fault tolerance. To effectively use cache in software engineering system design, software engineers must carefully consider the cache design, including the size of the cache, the eviction policy, which determines how data is removed from the cache, and the cache consistency model, which determines how data is updated and invalidated. Security is also a critical consideration in cache design, as cache can potentially contain sensitive data. Software engineers must ensure that cache data is protected against unauthorized access and that cache security mechanisms such as encryption and access control are in place. In summary, cache is a mechanism used in software engineering systems designed to improve the performance of applications by storing frequently accessed data in a fast temporary storage area. It can be implemented at different levels of a system and used in different techniques such as key value stores or object caches. To effectively use cache in software engineering systems design, software engineers must carefully consider cache design, including size, eviction policies, consistency model, and security mechanisms. Weather queues are a software engineering system design concept that allow different parts of a system to communicate asynchronously by sending messages to each other through a messaging system. A message queue acts as a buffer between the sender and the receiver, allowing messages to be processed at different rates and times. In a message queue system, messages are sent to a queue by sender and then retrieved by one or more receivers. The messages are processed by receiver in the order they were received and can contain data or instructions for the receiving system to act on. Message queues can provide several benefits in software engineering system design, including improved scalability, flexibility, and fault tolerance. By decoupling the sender and receiver, message queues can handle high volumes of messages without overwhelming the receiving system. They can also provide a mechanism for handling intermittent connectivity and allow systems to continue operating even if some of the parts are temporarily unavailable. In terms of software engineering systems design, message queues must be designed to be scalable, fault tolerant, and secure. This can be achieved by implementing multiple message brokers using load balancing to distribute traffic across them and configuring the message brokers to handle message routing and delivery. Security is also a critical consideration in message queue design, as message queues can potentially contain sensitive data. Software engineers must ensure that the message data is protected against unauthorized access and that message security mechanisms, such as encryption and access control, are in place. In summary, a message queues are a software engineering system design concept that allow different parts of a system to communicate asynchronously by sending messages to each other through a messaging system. They can provide several benefits including improved scalability, flexibility, and fault tolerance. To effectively use message queues in software engineering systems design, software engineers must carefully consider message queue design, including scalability, fault tolerance, and security mechanisms. Communication protocols are a set of rules and standards that govern the exchange of data between two or more devices or systems. In software engineering systems design, communication protocols are used to ensure that data is transmitted reliably, efficiently across different networks and devices. Network protocols are a type of communication protocol that defines how data is transmitted over a network. There are several different network protocols, including HTTP, Hypertext Transfer Protocol, UDP, User Datagram Protocol, and TCP, Transmission Control Protocol. HTTP is a network protocol used for transmitting web-based data, such as web pages and media files. It is the foundation of a World Wide Web and is widely used in software engineering systems designed for web-based applications. UDP is a network protocol used for transmitting data over a network with low latency and high speed, but with less reliability than other protocols. It is often used for real-time applications such as video streaming and online gaming. TCP is a network protocol used for transmitting data over a network with high reliability and error correction. It is commonly used for applications such as email and file transfers. In software engineering systems design, the choice of a communication protocol depends on the specific requirements of the application. For example, applications that require high speed and low latency may use UDP, while applications that require high reliability and error correction may use TCP. To effectively use communication protocols in software engineering system design, software engineers must carefully consider the requirements of application and choose the appropriate protocol accordingly. They must also optimize the protocol settings and network configurations to ensure that data is transmitted reliably and efficiently. Security is also a critical consideration in communication protocol design, as communication protocols can potentially be vulnerable to various types of attacks such as man-in-the-middle attacks and packet sniffing. Software engineers must ensure that the communication protocol security mechanisms such as encryption and authentication are in place to protect against these types of attacks. Security is a critical consideration in software engineering system design, as software systems can be vulnerable to various types of attacks such as data breaches, DDoS attacks, and malware infections. Security in software engineering system design refers to the measures and strategies used to protect the confidentiality, integrity, and availability of software systems. To ensure security in software engineering system design, software engineers must carefully consider security risk and implement security mechanisms such as access control, encryption, and intrusion detection. They must also design the software system to be resilient against attacks, including implementing backup and recovery mechanisms and conducting regular security audits. Access control is a critical security mechanism that regulates access to software systems, ensuring that only authorized users can access the system. This can be achieved through user authentication and authorization mechanisms, such as username and password, two-factor authentication, and role-based access control. Encryption is another critical security mechanism that protects data against unauthorized access. Encryption works by transforming data into a format that can only be decrypted by authorized users with the appropriate encryption key. Intrusion detection mechanisms such as firewalls and intrusion detection systems can detect and respond to attacks on software systems. These mechanisms can monitor network traffic, identify suspicious activity, and automatically respond to potential threats. Software engineers must also consider security when designing the software architecture and implementing the software modules. This includes designing for resilience and failover, implementing secure coding practices, and regularly testing and auditing the software system for security vulnerabilities. In summary, security is a critical consideration in software engineering system design, and it includes implementing security mechanisms such as access control and encryption, designing for resilience and failover, and conducting regular security audits. Software engineers must carefully consider security risk and implement measures to protect the confidentiality, integrity, and availability of software systems. Consistent hashing is a technique used in software engineering system design to distribute data across multiple servers or nodes in a distributed network. In consistent hashing, a hash function is used to map each piece of data to a point in a circle, with each server represented by a point on the same circle. And when data needs to be stored or retrieved, the hash function is used to map the data to a point on the circle, and then the data is stored or retrieved from the server corresponding to the next point on the circle. This ensures that each piece of data is consistently mapped to same server. Even if the number of servers in the network changes, consistent hashing can provide several benefits in software engineering system design, including improved scalability, fault tolerance, and load balancing. By distributing data across multiple servers, consistent hashing can improve scalability and allow for more efficient use of resources. It can also provide fault tolerance by allowing data to be replicated across multiple servers so that if one server fails, the data can still be accessed from another server. Load balancing can also be achieved by adding or removing servers from the network without needing to remap all of the data. In terms of a software engineering systems design, consistent hashing must be carefully designed to ensure that the hash function is efficient and that the distribution of data is balanced across the servers. Software engineers must also ensure that the consistent hashing system is fault tolerant and can handle server failures and network disruptions. In summary, consistent hashing is a technique used in software engineering system design to distribute data across multiple servers in a distributed network. It provides several benefits including improved scalability, fault tolerance, and load balancing. To effectively use consistent hashing in software engineering system design, software engineers must carefully design the hash function and ensure that the system is fault tolerant and can handle server failures and network disruptions. API Gateway is a software engineering systems design concept that provides a centralized entry point for accessing multiple APIs, application programming interfaces. An API gateway acts as a reverse proxy routing request from the clients to the appropriate backend services and handling tasks such as authentication, rate limiting, and caching. In API gateway architecture, the gateway provides a single endpoint for accessing multiple backend services, which can be implemented using different programming languages or protocols. The gateway can perform several functions such as a routing request, translating between different protocols or message formats, and performing security checks. API Gateway can provide several benefits in software engineering systems design, including improved security, performance, and scalability. By centralizing access to multiple APIs, API Gateway can provide security by providing a single point of control for authentication and authorization. It can also improve performance by reducing the number of network hops required to access backend services and by caching frequently accessed data. Finally, API Gateway can improve scalability by providing a layer of abstraction between the clients and backend services, allowing backend services to be added or removed without affecting client applications. To effectively use API Gateway in software engineering systems design, software engineers must carefully design the gateway architecture, including choosing appropriate protocols and message formats, and implementing security and caching mechanisms. They must also ensure that the API Gateway is scalable, fault tolerant, and can handle high volumes of requests. In summary, API Gateway is a software engineering system design concept that provides a centralized entry point for accessing multiple APIs. It can provide several benefits, including improved security, performance, and scalability. To effectively use API Gateway in software engineering system design, software engineers must carefully design the gateway architecture, implement security and caching mechanisms, and ensure that the gateway is scalable and fault tolerant. Microservices is a software engineering systems design concept that involves breaking down a software system into smaller independent services that can be developed, deployed, and maintained separately. Each microservice typically performs a specific function within the system, such as handling user authentication or processing payments. Microservices architecture is designed to improve scalability, flexibility, and maintainability of software systems by breaking down a monolithic system into smaller services. Microservices architecture allows for more efficient use of resources and can enable faster development and deployment cycles. It can also allow each service to be deployed and tested independently, making it easier to maintain and update the system over time. In microservices architecture, each microservice communicates with other microservices through APIs or message queues. This allows the system to be easily scaled and updated without affecting other parts of the system. However, microservices architecture can also introduce new challenges such as increased complexity in managing multiple services and coordinating interactions between them. It also requires careful consideration of security, as each microservice can potentially be vulnerable to attacks. To effectively use microservices in software engineering systems design, software engineers must carefully design the system architecture and consider factors such as service granularity, communication protocols, and security mechanisms. They must also ensure that the system is scalable, fault tolerant, and can handle high volumes of requests. In summary, microservices is a software engineering systems design concept that involves breaking down a software system into smaller independent services. It can provide several benefits, including improved scalability, flexibility, and maintainability. To effectively use microservices in software engineering systems design, software engineers must carefully design the system architecture and consider factors such as service granularity, communication protocols, and security mechanisms. In software engineering system design, services can be categorized as either stateless or stateful based on how they handle data and state. Stateless services are services that do not store any data or state information between the requests. Instead, each request is treated as a completely separate transaction with all the required data and state information provided in the request. Stateless services are often used for simple, fast transactions such as serving static web content. Stateful services, on the other hand, maintain state information between the requests. Stateful services can store data and state information in memory or in a database, allowing the service to remember previous requests and respond accordingly. Stateful services are often used for more complex transactions such as processing payments or managing user accounts. Stateless services can provide several benefits in software engineering system design, including improved scalability, fault tolerance, and flexibility. By not storing any data or state information, stateless services can handle large volumes of requests without becoming overwhelmed. They are also more fault tolerant as they do not rely on persistent data storage. Finally, stateless services are more flexible as they can be easily added or removed from a system without affecting other services. Stateful services, on the other hand, can provide benefits such as improved performance, reliability, and consistency. By maintaining the state information between the requests, stateful services can provide faster response times and more accurate data. They are also more reliable as they can recover from failures and continue processing requests without losing any data or state information. To effectively use stateless and stateful services in software engineering systems design, software engineers must carefully consider the requirements of application and choose the appropriate service type accordingly. They must also ensure the system architecture is designed to handle both stateless and stateful services, and that security mechanisms are in place to protect sensitive data and state information. Service discovery is a software engineering system design concept that involves automatically locating and identifying services in a distributed network. In a distributed system, services may be spread across multiple servers or nodes, making it difficult to know where specific services are located. Service discovery provides a mechanism for finding services and establishing connections between them. Service discovery can be achieved through various methods, including DNS-based discovery, client-side discovery, and server-side discovery. So DNS-based discovery involves using DNS records to locate services, while client-side discovery involves client contacting a registry or load balancer to locate services. Server-side discovery involves the server providing a list of available services to the client. Service discovery can provide several benefits in software engineering systems design, including improved scalability, fault tolerance, and maintainability. By automating the process of locating services, service discovery can improve scalability by allowing new services to be added or removed from the system without requiring manual configuration. It can also provide fault tolerance by automatically redirecting the request to available services if a service fails. Finally, service discovery can improve maintainability by allowing services to be easily updated or replaced without disrupting the overall system. To effectively use service discovery in software engineering system design, software engineers must carefully design the system architecture and choose appropriate service discovery mechanisms. They must also ensure that the system is fault tolerant and can handle service failures and network disruptions. Finally, they must ensure that security mechanisms are in place to protect sensitive data and prevent unauthorized access to services. In summary, service discovery is a software engineering system design concept that involves automatically locating and identifying services in a distributed network. It can provide several benefits, including improved scalability, fault tolerance, and maintainability. To effectively use service discovery in software engineering system design, software engineers must carefully design the system architecture and choose appropriate service discovery mechanisms and ensure that the system is fault tolerant and secure. Web servers and application servers are both software components used in software engineering system design to deliver web applications to clients. A web server is a software program that is responsible for receiving HTTP requests from clients, such as web browsers, and returning HTTP responses containing web content such as HTML pages, images, or files. A web server typically runs on a dedicated server computer and may be responsible for serving multiple web applications simultaneously. An application server, on the other hand, is a software program that is responsible for executing the business logic of an application, typically using a server-side scripting language such as Java or PHP. An application server also provides services such as database access, security, and messaging. Application servers can run multiple applications simultaneously and often use middleware to facilitate communication between different components. In terms of software engineering systems design, the choice between a web server and application server depends on the specific requirements of the application. For simpler applications, a web server may be sufficient to deliver content to clients. For more complex applications that require server-side processing, an application server may be required. Web servers and application servers can also be used together in a hybrid architecture. In this architecture, the web server handles client requests and returns static content, while the application server handles dynamic content generation and processing. This architecture can provide benefits such as improved performance, scalability, and security. To effectively use web servers and application servers in software engineering system design, software engineers must carefully design the system architecture and choose appropriate server software and middleware. They must also ensure that the system is scalable, fault tolerant, and can handle high volumes of requests. Finally, they must ensure that security mechanisms are in place to protect sensitive data and prevent unauthorized access. Worker servers are a type of server used in software engineering system design to perform background processing tasks such as data processing, message queue processing, and batch jobs. Worker servers are typically designed to handle long-running processes as well as processes that may require significant processing power or memory. In a distributed system, worker servers can be used to offload processing tasks from other servers such as web servers or application servers, freeing up resources for handling user requests. And this can improve performance and scalability by allowing the system to handle more concurrent requests and reducing response times. Worker servers can be implemented using a variety of programming languages and technologies, including Java, Python, Ruby, and Node.js. They can also use middleware such as message queues or task queues to manage and prioritize tasks. To effectively use worker servers in software engineering system design, software engineers must carefully design the system architecture and choose appropriate server hardware and software. They must also ensure that the system is fault tolerant and can handle server failures and network disruptions. Finally, they must ensure that security mechanisms are in place to protect sensitive data and prevent unauthorized access. Worker servers can provide several benefits in software engineering system design, including improved performance, scalability, and fault tolerance. By offloading processing tasks to worker servers, the system can handle more concurrent requests and respond faster to user requests. It can also be more fault tolerant as worker servers can continue processing tasks even if other servers fail. In summary, worker servers are a type of server used in software engineering system design to perform background processing tasks. They can provide several benefits, including improved performance, scalability, and fault tolerance. To effectively use worker servers in software engineering system design, software engineers must carefully design system architecture and choose appropriate server hardware and software, and ensure the system is fault tolerant and secure. API servers. Application Programming Interface servers are a type of server used in software engineering system design to provide access to web services and data. An API server exposes a set of RESTful representational state transfer endpoints that clients can use to interact with the system and retrieve or manipulate data. In a distributed system, API servers can be used to provide a centralized interface for accessing multiple services and data sources. This can improve performance and scalability by reducing the number of network hops required to access data and services, and by allowing clients to access data in a standardized way, API servers can be implemented using a variety of programming languages and frameworks such as Node.js, Python, Ruby on Rails, and Spring Boot. They can also use middleware such as load balancers, caching layers, and rate limiters to manage and optimize API requests. To effectively use API servers in software engineering system design, software engineers must carefully design the API architecture and choose appropriate server hardware and software. They must also ensure that the API is secure and can handle high volumes of requests, and that API documentation is provided to help clients understand how to use the API. API servers can provide several benefits in software engineering system design, including improved performance, scalability, and standardization. By providing a centralized interface for accessing data and services, API servers can simplify client interactions with the system and improve performance by reducing the number of network hops required. They can also provide a standardized way of accessing data, making it easier for clients to understand and use the system. In summary, API servers are a type of server used in software engineering system design to provide access to web services and data. They can provide several benefits, including improved performance, scalability, standardization. To effectively use API servers in software engineering systems design, software engineers must carefully design the API architecture and choose appropriate server hardware and software, and ensure that the API is secure and well documented. Polling, long polling, and WebSockets are different techniques used in software engineering systems design to enable real-time communication between clients and servers. Polling is a technique where the client regularly sends requests to the server to check for new data or updates. This can be an inefficient technique as it can result in a large number of unnecessary requests to the server. Long polling is a variation of polling where the server waits to respond to the client's request until new data or updates are available. This reduces the number of requests the client needs to make, resulting in a more efficient communication system. WebSockets are a more advanced technique that allows for real-time bidirectional communication between clients and servers. WebSockets use a persistent connection that allows for data to be sent in both directions without the need for a repeated request. In software engineering system design, the choice between these techniques depends on the specific requirements of the application. Polling is a simpler technique. Polling is a simpler technique that may be suitable for applications with low traffic or infrequent updates. Long polling may be more appropriate for applications with higher traffic or where updates are more frequent. WebSockets are ideal for applications that require real-time communication or collaboration between clients and servers. To effectively use these techniques in software engineering system design, software engineers must carefully design the communication architecture and choose appropriate communication protocols and technologies. They must also ensure that the system is scalable, fault-tolerant, and can handle high volumes of requests. In summary, polling, long polling, and WebSockets are different techniques used in software engineering system design to enable real-time communication between clients and servers. The choice between these techniques depends on the specific requirements of the application, and software engineers must carefully design the communication architecture and choose appropriate communication protocols and technologies to effectively use them.